think about the shape of a molecule like methane, tetrahedral molecule with bond angles between every hydrogen to carbon to hydrogen of 109.4 degrees, it doesn't really fit with atomic orbital theory. Atomic orbital theory with s orbitals and p orbitals, which are of different shapes and sizes. How do we get a symmetrical molecule like methane if we're using atomic orbitals of different shapes for chemical bonding? We can explain the symmetrical nature of methane with equal bond angles every time by using hybridization theory. In hybridization theory, we use the ideas that if a particle can act like a wave, then a wave can act like a particle. And we're thinking about these orbitals and treating them as wave functions. Wave functions which can come together constructively, just like any water wave, and produce a bigger wave when they're in phase together, or come together destructively or out of phase, and at least partially or completely cancel each other out. So let's look at sp3 hybridization. So we're taking these atomic orbitals, the s and the 3p atomic orbitals, hence the name sp3, and we combine them together like wave functions to produce 4 new sp3 hybrid orbitals. So the colours and positives and negatives are just trying to represent whether the waves are coming together constructively or out of phase and destructively. And as they come together, the hybrid orbitals which are produced are focused on one side of the nucleus. When they're reinforced and come together in phase constructively, and on the other side, when they've come together out of phase. So, as we move through the chapters, we're going to simplify this picture and just omit this out of phase left-hand side of the hybrid orbital. But it's really there, and we're just tidying up our pictures a bit. So these sp3 hybrid orbitals focus the orbital area on just one side of the nucleus. From sp3 hybridization, we produce 4 of these sp3 hybrid orbitals. So for example of methane, the s and the 3p orbitals, when combined together to give 4 equal hybrid orbitals of equal energy and shape, it gives us 1 electron in each of these hybrid orbitals, an electron which allows it to overlap with a neighbouring hydrogen atom and form a chemical bond and make 2 electrons in each bond. We can also show this idea of sp3 hybridization for atoms like oxygen and also nitrogen. The s and the 3p atomic orbitals coming together in phase constructively to produce the 4 new sp3 hybridized orbitals. Each of these new orbitals, which are equal in energy, they're all called an sp3 hybrid orbital because we use an s and 3p atomic orbitals to make them come into existence. And it gives us 4 orbitals of equal energy, and they space themselves out symmetrically around the nitrogen atom. And one of those hybrid orbitals is going to be used normally to hold the lone pair of electrons, giving us 3 orbitals for chemical bonds to neighbouring atoms. With sp2 hybridization, this time we're taking an s orbital and just 2 of the p atomic orbitals and combining them together like wave functions, and they come together constructively to produce these 3 orbitals of equal energy, 3 sp2 hybridized orbitals, which therefore gives us one atomic p orbital, which is not hybridized, and our three hybrid orbitals are arranged in a trigonal planar arrangement around the nucleus of the carbon, with a bond angle each time of 120 degrees between each hybrid orbital, and the last atomic orbital fits in above and below the plane at 90 degrees to each of the hybrid orbitals. And we'll see in the future that these atomic orbitals are used when carbon and carbon atoms come together to form pi bonds or double bonds. And that electron density is shared between the atomic orbitals of the two atoms above and below the plane of the two nuclei. The plane of the two nuclei, of course, is where that original carbon-to-carbon single bond using hybrid orbitals is keeping its electrons. Our last example of hybridization is sp hybridization, aptly named because we use just the s and 1 of the p atomic orbitals to perform the hybridization. The orbitals come together as wave functions, and they combine to produce two new hybrid orbitals. For every atomic orbital used in the hybridization, we get a hybridized orbital coming out. And these two hybrid orbitals, these two sp hybrid orbitals, arrange themselves linearly around the nucleus of the atom with a bond angle between the orbitals of 180 degrees. They keep the orbitals as far away from each other as possible, maximizing distance between pairs of electrons, be it lone pairs or bonding pairs, and that will minimize repulsion. The two atomic orbitals, the p atomic orbitals, which were not hybridized, the first one, as we saw in sp2, is above and below the plane. And the second one, trying to get as far away from the hybrid orbitals and the atomic orbitals as much as possible. The second one is going into the board and coming out of the page. 90 degrees angles to each of the other atomic orbitals and hybrid orbitals, keeping the molecule as symmetrical as possible. And we can normally identify an sp hybridized atom because it's probably going to be a carbon atom which is involved in a triple bond. And it's these atomic orbitals, 2 atomic orbitals, which are used with an adjacent atom with 2 unhybridized orbitals to form that double and triple bond. In the hybrid orbitals, with direct overlap between the 2 atoms, these hybrid orbitals form the original carbon-to-carbon single bond. To summarize our hybridization, we're only looking at 3 kinds over the entire semester. sp3 hybridized, when we use all of the atomic orbitals to produce 4 new hybridized orbitals. They space themselves out as far as possible to give us the 109.4 bond angle or orbital angle, making up the normal tetrahedral shape of a carbon in methane. When one of the atomic p orbitals is unhybridized, we therefore have just sp2. And the 3 hybridized orbitals arrange themselves in a trigonal planar shape around the central atom with the atomic orbital above and below the plane. And this is the type of hybridization we normally see for an alkene molecule with a carbon-to-carbon double bond on those 2 particular carbons. And then our sp hybridization for carbon-to-carbon bonds, which are triple bonds with just 2 hybrid orbitals in a linear arrangement around that particular carbon atom. Therefore, we have 2 atomic p orbitals which can be used for a double and triple bond in the molecule.